Hello, everyone. My name is Han, a lecturer from the University of Adelaide. I'm very happy to give this presentation about the behavior of geopolymer concrete filled circular steel tip members. The research was performed collaboratively with my colleague, Associate Professor Phillip Visintin. The research was driven by the urgent needs to develop sustainable infrastructures because the current infrastructure construction leads to significant environmental impacts. The building and construction industry bring infrastructures that support operation of the society. We rely on the infrastructures for the quality of our life. So the construction industry is normally of very large scale in different countries around the world. Take Australia as an example. The industry brings 360 billion in revenue and creates more than a billion jobs. But the construction activities lead to a lot of environmental problems, such as 23% of the air pollution, 50% of the climate change, 40% of the drinking water pollution. The construction consumes 40% of the global use of raw materials. As shown in the figure on the right hand side, the construction activities at different stages leads to CO2 emission. And the research has shown that the construction industry is one of the main contributors to the greenhouse gas emission and the climate change. As we are all aware of the severe environmental deterioration, we need to work towards the global target for the net zero emission in 2050 to have green futures. To realize sustainable and low carbon infrastructures, we then need to look at where the problems of where significant greenhouse gas emission or environmental problems were generated. And the research shows that one of the main causes would be the use of concrete. The concrete is the second most consumed material after water, and we consume 25 billion tons of concrete used globally every year. But the concrete is made from Portland cement as the binder, but the Portland cement production leads to high greenhouse gas emission. Producing 1 ton of Portland cement leads to about 1 ton greenhouse gas emission. And this emission is caused by the fabrication process as the calcination of the limestone. And this process not only generates CO2 emission itself, but also consumes significant amount of energy from fossil fuel combustion, which also causes greenhouse gas emission. The research has been performed to determine the CO2 emission due to the cement production every year, and the results is very impressive. Like in 2019, the global CO2 emission due to cement production is 1,500 megaton. By understanding the significant problems caused by the use of concrete, we then start to have the research initiation to look for eco-friendly and low carbon material for our infrastructures to reduce the greenhouse gas emission due to the use of concrete. So with this motivation, eco-friendly geopolymer concrete was developed. The geopolymer concrete can be generated through the process um, shown on the right-hand side as a series of chemical reactions. So the geopolymer concrete was generated using the industry byproducts such as fly ash and GGBFS with aluminosilicate rich materials, and these materials are reacted with alkaline solutions to generate geopolymer concrete. The research performed by my colleague Philip has shown that the geopolymer concrete um, and its production leads to much reduced greenhouse gas emission in comparison with the Portland cement concrete. But in order to use geopolymer concrete to form structures for our infrastructures, we need to examine the structural performance. But existing studies mainly focus on the geopolymer concrete structures reinforced by steel or FRP bars. And the research shows that these structures experience brittle failures and very low ductility, especially for the columns. The ultimate loss of the resistance reduced all of a sudden, once the peak load was reached, and the load dropped by 90% or even 100% due to the brittleness, the brittle fate of the structure, as shown on the right-hand side of the spalling of the geopolymer concrete. One way to improve the structural performance and ductility that is favorable for the design, especially for the infrastructures in the earthquake-sensitive zone, is applying steel tube to generate confinement to the geopolymer concrete to form the geopolymer concrete filled steel tube structures as shown on the right-hand side. The steel tube can provide confinement to improve the strength and ductility of the geopolymer concrete. But we need to justify whether or not this structural system provide us with good structural performance, and we also need reliable design approaches for these structures in order to implement them in practice. So then it comes to the aim of this study to investigate the structural performance of geopolymer concrete filled steel tube members on the combined compression and bending, and to develop design approaches for the members. This combined compression and bending scenario was considered because it is the common loading condition considered for the structural design for typical applications such as building columns, bridge piers, and etc. The behavior of the structures was investigated using the methodology of combined experiments and numerical modeling. In the experimental investigations, we prepared a number of geopolymer concrete filled circular steel tube members, and we test them on the different types of loading. We tested one on the concentric compression, one on the 3-point bending using the test setup shown in the photo at the bottom, and we tested a number of specimens on the combined compression and bending by applying compression with different eccentricities to generate different bending to compression ratios. The test on the concentric and eccentric compression was performed using the setup on the right-hand side. Each member was tested on the pin end conditions, and we used LVDTs and strain gauges to trace the deformation responses of the structure when the load was increased and decreased through displacement control. Due to the time limit of this presentation, I just wish to show some key results and observations from the experimental investigations. From the experiments, we measured the load versus deformation responses for different specimens. The figure near the top shows the plots of the compressive load versus the mid-head deflection measured from the LVDTs. It shows that the structures undergo increasing mid-head deflection in a linear way with increasing load. But once the ultimate loads were reached, the load or the resistance degrades gradually without sudden drop of the capacity. So the structure demonstrates very good ductility, indicating the effective confinement from the steel tube. The results shown in the figure near the bottom were obtained for the member subject to the 3-point bending. The structural performance is similar to the conventional concrete filled steel tube beams with the Poland cement-based concrete infill. So you can see that the load was sustained around the ultimate level with increasing mid-span deflection. Failure modes of the structures were also observed from the test. Global buckling happened to the members on the concentric and eccentric compression. Overall bending failure was observed for the specimen subject to 3-point bending. And to investigate the geopolymer concrete core within the steel tube, I cut one specimen open after testing, as shown in the figure near the bottom on the right-hand side. As you can see from the photo, the geopolymer concrete maintained its integrity without the severe spalling observed by other researchers when the structure was reinforced inside by bars. On the tensile side, I observed some minor transverse tensile cracks So it shows that the steel tube provides quite effective confinement to the geopolymer concrete. Apart from the experimental investigation, I also performed a numerical simulation because it is more cost efficient to perform the investigation on a large number of geopolymer concrete structures in numerical simulation. So I firstly developed the FE model in ABACUS by incorporating the material properties from the steel tube and the geopolymer concrete infill. For the geopolymer concrete in particular, I developed the stress-strain relationship with the confinement effect incorporated. Surface-to-surface contact was considered for the interaction between the steel tube and the geopolymer concrete infill. Geometric imperfections were considered in the model, and boundary conditions were also applied according to the test arrangements. The FE model was first validated using the experimental results I obtained through the research. And just to show a typical example of the FE model validation for a member tested on the eccentric compression with the eccentricity of 30 mil. As can be seen in this figure, the FE model can replicate the experimental results. And on the right-hand side, you can see that the global buckling failure was accurately traced by the FE model. So upon the validation of the FE model, I can then perform systematic parametric studies to investigate the influence of different parameters on the structural performance of the geopolymer concrete field circular steel tube members on the combined loading. I can consider different geometric properties such as the diameter to thickness ratios of the steel tube or different material strengths for the steel tubes or etc. So just to show one set of results from the parametric studies in the plots shown in the middle. So it's the results for the members with the steel tube with a varying diameter to thickness ratio. And it shows that the structures with lower diameter to thickness ratios for the steel tube provide higher resistance to the combined compression and bending as the red color curve. So these compression and bending curves, the pattern is very comparable to those curves of the conventional concrete field steel tube structures. And by decreasing the diameter to thickness ratios, actually the steel ratios within the cross section increases. So higher strength contribution from the steel tube are obtained for the structures, so that higher resistance to the loads were obtained. So apart from the understanding into the structural performance in the experimental and numerical research, I also performed the evaluation of or development of design approaches because we need reliable design approaches for the geopolymer concrete field steel tube structures in order to implement that for the low carbon infrastructure construction. So what I did was to evaluate the interaction diagrams and specifications in design codes for conventional concrete field steel tubes with the infill of Portland cement-based concrete. The interaction diagrams from Eurocode and American standards are shown in the plot in the two figures. And I demonstrate an example of the design load estimation for a specimen tested on the eccentric compression with eccentricity of 60 mil, as shown in the figures. So you can see that the design loads from Eurocode or American standards is lower than the ultimate load measured for the specimen in experiments. So this indicates that the existing design methods can be used to generate conservative strength predictions. So subsequently, I performed the statistic evaluation of the design codes using the experimental results I obtained, as well as the results from the parametric studies. So the evaluation outcomes are shown in the table put at the bottom. On average, the design approaches in these standards provide conservative strength predictions so they can be safely applied to the design of the circular shape geopolymer concrete field steel tube structures. Compared with American standard Eurocode before is more accurate. So that's the main part of the presentation that I wish to talk about. So finally, I wish to draw the conclusions. So this research mainly investigates the behavior of geopolymer concrete field circular steel tip members with high potential for low carbon structure construction to reduce the environmental impacts due to structural construction. Good structural strength and ductility are observed for the structures, and the experimental results are used as the basis for validating the FE model for subsequent systematic parametric studies. The mechanism of the structures was investigated and found to be about the same as that for the conventional structures with the infill of ordinary Portland cement concrete. And apart from the investigation into the mechanism, I also examined the applicability of existing design codes to the concrete geopolymer concrete field steel tip structures, and found that these design codes can be applied to generate safe design for the structures. So that's the end of my presentation. Thank you.